When you build a backend application, your engineering team sees an architectural choice. But your operating system doesn't see a web app at all. It sees a process, an isolated, resource-hungry sandbox fighting for survival on a bare metal. Most engineering teams choose their tech stack based on syntax comfort or developer familiarity. But synthetic Hello World benchmarks are a lie. They don't account for what happens under extreme production stress. In this playlist, we are going to run two highly rigorous production-grade architectural experiments. The event loop death test is the first one. We will show exactly how a single CPU-heavy operation can completely freeze Node.js and Python, sending P99 latencies through the roof, while Go's scheduler handles the exact same load effortlessly. The second experiment is the $10,000 cloud build test. We will choke identical backend configurations with 10,000 concurrent webhooks to demonstrate how process duplication in Python and Node translates directly into massive bloated enterprise cloud infrastructure's expenses. We all know about the builds, right? But here is the reality. Directly jumping into these benchmarks won't make you a better architect. If you want to make serious multi-million-dollar tech decisions, you need to know how the machine actually thinks. This is why this playlist is built differently. Before we deploy a single line of test code, we have designed an 8-part foundational series. We will strip away the abstractions and look under the hood of modern operating systems. By the end of this journey, whether you are a tech founder, a CTO protecting margins, a product manager managing reliability, or a developer aiming for a senior role, you will possess the mental models needed to confidently defend your architectural choices against any tech stack hype. To understand why we need these benchmarks, we have to look back at how computers traditionally handled backend applications. Historically, servers treated hardware resources with brutal inefficiency. In the early days of web engineering, software architectures frequently relied on a thread per request model. When a user is connected to your server, the operating system spawned a dedicated thread and allocated a chunk of physical RAM just to track that individual user's session. Under light traffic, this worked fine. But scale changes physics. Throw thousands of simultaneous users at a thread per request architecture, and your system encounters a catastrophic resource wall. The RAM consumption spikes exponentially, but worse, the CPU spends more time running context switching. This means it saves and loads thread states in memory than it does executing actual application's logic. Different languages emerged to solve this exact hardware crunch in fundamentally different ways. Node.js introduced a single-threaded asynchronous event loop to bypass the thread per request limitation of I/O tasks. I/O tasks means input and output. User sends the input, backend sends the output. Python doubled down on developer speed but bound itself to the global interpreter lock, which is also called GL, necessitating complex multiprocessing to scale across CPU cores. We'll come back to this later on. Go completely shifted the paradigm by implementing an ahead-of-time compiler and its own low-overhead user space and work stealing scheduler. Again, I'll explain the technical details later on. In our next video, we are starting at the absolute bedrock of system architecture: user space versus kernel space. We will uncover the hidden boundary lines your code must cross via system calls just to talk to the physical hardware beneath it. Hit subscribe, open your terminal, and let's dive into the machine.